And I'll get the share screen going. Oh, no, it's not cooperating. That's weird. It says unable to connect. That's not what I like to hear. Let's try again. Still saying unable to connect. Well, we might be doing model theory by charades or something today. I'm resetting the iPad. Might take a moment.
Nick, one thing you can try is connecting your iPad as a second user to the Zoom call and then sharing a screen from there.
Oh, really? Is that better?
That's what I do in my discussions, and it works. So it's something to try. I don't know.
Yeah, maybe I should invite myself. Okay. Anyway, the iPad has restarted, so if it works, then we'll do that, and if it doesn't work, then I'll try this other method. Yeah, it's not working. Oh wait, now it's back. Okay, so I think we're good. So next time I might try to log in a different way. All right, so let's just remember very briefly what a Ramsey class of finite structures does. Oh no, I mean, Zoom is working fine, but okay, now my Apple Pen is dead. I did charge it. Well, today's not a very good day.
When you restart your iPad, it sometimes disconnects and you have to reconnect the pencil.
Aha, maybe that's the issue. Let's see, settings, Bluetooth, Apple Pencil connected. Okay, it might just be dead. Let's see, notability. Okay. Okay, great. Now we're in fantastic shape, and everyone, is fresh. You got a little break, so let's do some model theory. So, okay, let's just remember what this notation says. So, this says, whenever you have a structure C, and you have some coloring with R values on all the copies of A sitting inside. Then you can find sitting inside of C some copy of B such that all the copies of A sitting inside have the same color. Like maybe they're all red. Okay. So the C here is like the big structure, and you're calling all of its copies of A. And then B is like some smaller structure, which is going to be the homogeneous set. This is going to be the structure such that all of the A's sitting inside get the same color. Okay, is this clear? It works just like regular Ramsey's theorem, except now you have structures instead of subsets. All right, and then let's just remember the definition. So you say K is a Ramsey class. I'm assuming here that K is a for say class. K is a Ramsey class if for every A contained in B in K, and r less than omega, there is some b prime, which is a copy of b living inside of C. Sorry. Let me just say it this way. There is C such that C arrows B, A, R. Okay. Now, let me just make an observation about this. So,
Nick, you want to say
because we'll use it at some point.
C and K, right?
Yes, thank you. C and K. It should be in the structure, or in the class of structures. Thank you. Let me just make an observation that we will use, which is that suppose so if K is a Ramsey class, then suppose I'm given two structures and some number of colors. So now I color all the copies of A1 and all the copies of A2. And I want all of the copies of A1 and all the copies of A2 to be homogeneous. How can I do that? So what I want is I've got some structure C. I have some copies of A and some copies of A prime sitting inside. And I color them separately. I have two colorings, one on the copies of A and one on the copies of A prime. Can I find a copy of B such that all the copies of A sitting inside of B get the same color and all the copies of A prime get some constant color? Is that possible? The answer is, of course, yes. I can do it by induction. So how do I do that? Well, what I can do is, for example, suppose C arrows C prime, A prime R, and C prime arrows B A R. So then what happens? So I have my copy of C, and I think just about the coloring on A prime. So I've got a whole bunch of A primes inside. And sitting inside, I find some copy of C prime. Such that all the A primes sitting inside of C prime get the same color. And then I had some coloring on C for all of the copies of A sitting inside of C. That restricts to give a coloring of all the copies of A sitting inside of C prime, right? Because C prime is a substructure of C. So now, instead of looking at the copies of A prime, I look at the copies of A sitting inside of here. So now I've got some copies of A sitting inside. And I restrict further to find some copy of B, such that all the copies of A sitting inside of B get the same color. And what do you notice? Well, every copy of A sitting inside of B gets the same color. That's how I chose this B. But also B is a substructure of C prime. So every copy of A prime living inside of B gets the same color. And so I can find a copy of B such that every copy of A and every copy of A prime gets, or get the same color. Of course, the coloring for A and the coloring of A prime have nothing to do with each other. So the color, the constant color that the A's take on might be different than the constant color the A primes take on. But every A sitting inside of B gets the same color. Every A prime sitting inside of B gets the same color. So I can do it for more than one structure at once if I want to, at the cost of making C bigger. Does that make sense? So, if I have in structures and I want all of these in structures to be monochromatic in a single structure, I can also do that. Okay. So it's just a remark. We'll use that at some point. All right. So before we can start talking about generalized indiscernibles, I just want to make one lemma concerning sort of the pure combinatoric stuff. So suppose K is a Versailles class. And F is a infinite structure, let's say countable, but I'm not sure that matters. Infinite structure with age K. Then K is a Ramsey class if and only if F arrows, well, let's say it this way, for all A subset of B in K and R less than omega, F arrows B superscript A sub R. Okay, so this says that you can use the infinite structure as the domain rather than some very large finite structure. And one comment to make is that when I said age F equals K, notice I did not say that F is homogeneous. So there are many structures that might have the same age. What Versailles' theorem said is that there's a unique one which is homogeneous, right? So that's the Versailles limit. So you can, if you have a Versailles class, you can build a countably infinite structure which has K as its age, but also has many automorphisms. So if you think about the class of finite linear orders, you can construct the rational numbers, which are homogeneous and have every finite linear order sitting inside. But of course, you can think about the natural numbers. As linear order, this is rigid. It has no automorphisms because it has the least element and it's a well order. But its age is K. It has every finite linear order sitting inside. So for this proposition, you only need that the age is the right age. You don't need that the structure is homogeneous. So the proposition doesn't apply to necessarily just to the Versailles limit. Okay, so let's prove this. So I think this is like a kind of nice compactness argument. So one direction is going to be easy. So K, a Ramsey class, implies F arrows B AR because C in K implies C embeds into F as age F, age F equals K. What do I mean? Well, suppose you have some coloring of all of the copies of A living inside of F. I'm just going to do this proof by picture because I think it's otherwise clear. So here I've got my very big structure, F, and I've colored all of its copies of A sitting inside. So here's A, here's A, here's A, here's A. And because K is a Ramsey class, I know that there exists some C that arrows B, A, R, right? Now that C, I can think of it as a substructure of F. So I can find some C living inside. Now my coloring on all of the copies of A living inside of F restricts to a coloring on all the copies of A sitting inside of C. That will have a homogeneous copy of B living inside. So the whole coloring had a homogeneous copy of B living inside. So this direction is very easy. If I know that looking at a finite structure like C is enough to get a homogeneous subset, then certainly looking at the entire thing will be enough to get a homogeneous subset. So that's that direction. Does that make sense? All right, so the other direction is going to be a kind of, well, it's going to be a more complicated argument using compactness. So suppose now K is not a Ramsey class. All right, and what does that mean? So then there is some number of colors and structures A subset of B in K, in K, such that whenever I take a C in K, there is a coloring. Let's call it chi sub C, which is coloring on copies of A living inside of C with R many colors, such that there's no B prime in copies of B and C with chi C restricted to copies of A in B prime constant. This is the negation of the Ramsey property. It says that whenever I take a finite structure, there's some coloring that witnesses that I can't find a homogeneous subset. Now, what we'll do is we will try, so the way you're thinking about this is you're thinking about these C's as finite approximations to your structure F, right? So what we're gonna do is we're gonna use these finite approximations and compactness to find a coloring on the whole collection of copies of A living inside of F, which will give us a contradiction. So what will we do? Well, what we'll do is we'll use compactness in the form of ultrafilters. So let U be a non-principal ultrafilter on age F such that set XE, which is going to be the D, which are like finite structures of F that it contain E, is in U for all E in age F. So you take a finite structure and you look at the cone above it. You look at all finite structures that contain that particular structure. That should be large. And the thing to notice is that, like, if you take E and E prime in age F, then whenever I take XE and I intersect it with, oops, let's go back. And I intersect it with XE prime, that's the same thing as XE E prime, where the brackets mean the structure generated by E and E prime. So if I take XE and I take XE prime, when does the structure contain both XE and XE prime? It can, when does it contain both E and E prime? It does so when it contains the structure generated by E and E prime. Now, because I'm assuming that we're working with a locally finite class, I hope I built that into the definition. If not, then I insist that it should be locally finite. Then this collection generates a filter. You can take intersections and you stay big. So because it generates a filter, you can assume that you have an ultrafilter which extends it. So you just take this filter, extend it to a maximal one, and then you get an ultrafilter in which all these things are large. So these sets are sort of like the analog of the Frichet filter, except now you have a more complicated underlying set. Okay, so what we'll do is define a coloring in the following way. So define chi, which will be a coloring on copies of A living inside of F with R many colors by we will say that chi of A prime is equal to I if and only if the C in age F such that chi of C A prime equals I is large. Okay, so like I said, you think about the C's in age F as finite approximations to F. So I take some A prime, and I can look at A prime sitting inside of other finite structures. So I have F, I take some A prime, which is a copy of A, and I can look at all kinds of C's that contain it, that are still finite. So something like this. Now, what I'm asking is if a large number of those, from the perspective of the ultrafilter, assign color I to this structure, then I say that it gets color I. So I'm using the ultrafilter to tell me how to assign the colors based on partitioning the approximations and deciding which one is big. Okay, so now let's get a contradiction. So towards contradiction, suppose there is B prime, which is a copy of B and F, such that chi restricted to the copies of A and B prime is constant with color, let's call it I star. If it's constant, it has to have some color. Now, what goes wrong? Then we can look at X sub B prime. Recall these are the finite structures that contain B prime. And we can take an intersection over all A prime, which are copies of A living inside of B prime. And what we'll do is we will intersect that with the C in age F, such that A prime is contained inside of C, and chi sub C of A prime equals I star. Now, what do I know about this set? Well, if I look just at this set, I know that this set is in U by the choice of U. I chose U so that all these X sub B's were inside U. So this is certainly inside U. Moreover, each one of these sets is also in U by the construction of the coloring. Because I said that a copy of A prime, or sorry, a copy of A living inside of F gets the color I, just in case the set of approximations to F, finite approximations to F that contain A prime, assign A prime the color I. So this also has to be inside of U. So here we have a finite intersection of sets inside of U. That's got to be in U. So this set is large. Now, the whole point of having this ultrafilter is one of the axioms of being an ultrafilter is that a set in the ultrafilter is not empty. So there's got to be some structure here. So there is some C in this set. Okay? Then what do you know? Well, you know that B prime is a copy of B living inside of C because C is in XB prime. So being in XB prime means that B prime is contained inside of C. So certainly B prime is a substructure of C, which is isomorphic to B. And we know that chi sub c restricted to the copies of A living inside of B prime is constantly I star by the fact that C lives in this intersection. And what does that mean? That means that it contradicts the choice of chi sub C, because chi sub C was chosen such that there was no such B prime. Okay, so that says that if you know that no finite bit will be enough to get a homogeneous set, then moving to the infinite structure doesn't help. Okay, and that's nice to know. Okay.
So I have a quick question. So about the definition of the coloring chi.
Sure.
So looking at it, it seems at least thinking about, say, the class of finite linear orders, it seems that most C will just not contain the A prime. So we're defining chi A prime. So I don't know.
Okay,
I'm
good,
looking at this definition and I'm
good. Yeah, so you're exactly right. I think it would be helpful to just add this condition that that A prime is contained inside of C. Thank you. I mean, and you need that. Now, why is that okay? Well, look at the structures that contain A prime. By choice of you know that that's a large set, because that's X A prime. So what this set does is it partitions A prime into finitely many pieces, and then one of those has to be large. But to your point, I mean, I don't actually think it's true that most won't contain A prime because of our choice of U. Because like, if suppose you had a large set which avoided A prime, then that would mean that its intersection with X A prime is empty, and it's not, because then it would be null filter. So I mean, the way I wrote it was correct, but you could add this condition and it would clarify, I think.
okay. Yeah, thanks.
No problem. Yeah. Okay. So that's it. Now let's talk about generalized indiscernibles. Which is where all of this was supposed to go. Now, we say, well, let's start by supposing I is an L prime structure. We say AI, I in I, is an I indexed indiscernible if whenever I take the quantifier free type of two tuples. So if, let me quantify these, I bar, J bar in I. So these are tuples, not necessarily elements. That's why I wrote the bar. This implies that the type of the things that they index, and this is the quantifier free type in L prime, the type of the things that they index, AI bar and AJ bar, are the same. Okay, so this just says, whenever I look at the indices, if I take two n-tuples of indices and they have the same quantifier free type, then the things that they index have the same type. Okay, so let's think about some examples. So one possibility for L prime is the language of linear order, and I can just be the natural numbers. Then an I-indexed indiscernible, sorry, I-indexed indiscernible is the same thing as an indiscernible sequence. Why? Well, the normal definition for indiscernible sequence says if I take two increasing intuples, then the things that they index are the same and have the same type. Now, you know, what this says is suppose I take two intuples and they have the same order type. They have the same quantifier free type in the language of order. Then the things that they index are the same. Why is that the same? Well, okay, what can you say with quantifier free formulas in the language of order? You can say when things are equal, and you can say when things are greater than each other. So, of course, if you have some equalities, you can contract the tuple because to assume that they're non-redundant. And then all you're left with are two tuples, two intuples in some linear order, which are scrambled perhaps. But the fact that the things that they index have the same type means that when you permute them to put them in order, the things that they have the same type. And that's equivalent to saying that you have an indiscernible sequence. So it's a very easy check to show that indiscernible sequences are the same as I-indexed indiscernibles when I is a linear order. Another example, which we've talked about so far, is you could just take L prime to be the language of equality. If you have the language of equality around, you can't even distinguish the order. What do you have? You have indiscernible. Okay. So now we want to, has my video frozen? It's frozen for me. No, you can see me? Okay, good. Well, I won't worry about it then.
It's frozen for me too, but it's not, the tablet's fine.
Okay, well, it's starting to lag, I think. Here, I'm gonna try stop the share and then start again. Okay, hopefully this will be better. Okay, great. So we have these two kinds of indiscernibles already. One of them is the indiscernible sequence, one is the indiscernible set, and these correspond to generalized indiscernibles for an appropriate choice of index model. And now the question is, okay, when can we find indiscernibles? So like I said, the goal is to understand when you can find indiscernibles that somehow closely resemble a choice of I-indexed tuples. And for that, there's a definition that Lynn Scow introduced in her thesis called the modeling property. So for this, we will say that suppose well, let's say it this way. Suppose I and J are L prime structures, and AI, I in I, BJ, J in J are same length tuples in our monster model. So we say BJ, J in J, is locally based on AI, I in I, if whenever phi is a formula. And let's say j bar is a tuple from j. Then if phi is satisfied by bj bar, that implies there is some I bar in I with the quantifier free type in L prime of j bar equals the quantifier free type of I bar, and phi of A I bar, wait, that's not how I's look, is satisfied. Okay, so what does this say? So what this says is if you have a formula that holds of some in tuple indexed by elements of j, then that meant that in I, that behavior had to be witnessed by something coming from AI. Now, it didn't have to come from the same tuple, but it had to come from some tuple with the same quantifier free type. And this notion, it looks a little bit hard to parse at first, but an easy observation is that suppose I is a linear order, then AI, well, let's actually say I is, just to be super concrete, let's say I is omega with less than. Then AI, I less than omega. I'm sorry, I'm doing this backwards. Let's say BI, I less than omega is locally based on AI, I less than omega, if and only if BI, I less than omega realizes the EM type of AI, I less than omega. Why? Let's consider why. So what was the EM type? The EM type was the formulas that hold on every increasing in tuple coming from my sequence. So suppose now I have some formula that holds on a tuple from BI, I less than omega. Now, without loss of generality, I can assume that that tuple is an increasing in tuple because I can contract the tuple so that there's no to an order. So after possibly changing the formula, I can assume that I have a formula and an increasing in tuple that holds on the BIs. Now, what does it mean that it holds on the BIs? Well, if the BIs realize the EM type, that means there had to be some increasing in tuple in the AIs, which satisfied the same formula. Because if it was false on every increasing in tuple from the AIs, then its negation would have gone into the EM type. So that implies that that you have this equivalence. I mean, going both ways is more or less the same argument. It's very straightforward. So this idea of being locally based is a kind of like generalized notion of realizing the EM type. Notice here, though, we're agnostic about what the actual index set is. So we don't think of the EM type in this, I mean, so the EM type is like it's a type, it's a partial type that has a certain number of variables. But here, we don't actually care what the index set is. We have J, we have I, and the only thing that we care about is that we can realize all of the quantifier free types coming from J in I. They don't actually have to be the same. Okay, so what we'll say is, and here's the key definition. So a structure well, recall that I is an L prime structure. So we say I indexed indiscernibles have the modeling property if and only if whenever we are given ai I in I, there is bi I in I, which is an I indexed indiscernible locally based on ai I in I. So what does this say? What this says is you have the modeling property, if and only if, whenever I hand you some tuples indexed by I can find some indiscernible tuples, indiscernible in the sense described above, which closely resemble the sequence I was given. So this is exactly what we've been dwelling on so far. So our main example is I being the natural numbers. Why? Well, we proved that whenever I take an infinite collection of tuples indexed by the natural numbers, say, that I can find an indiscernible collection of tuples which closely resemble the sequence I was given. That we proved twice. So this is the key example. This is the first example. But as we'll see, there are others. So the theorem, which is due to Scow, one of the main theorems in her thesis, is that okay, suppose I is an L prime structure, then I indexed let me say it, okay. I want to avoid some of Lynn Scow's assumptions, so I'm actually just going to write it this way. Age I, a for say class, then I indexed indiscernibles have the modeling property if and only if age I is a Ramsey class. Okay, so let's do one direction today, and then we'll finish up the next time. So what direction should we do? Well, okay, let's do the direction that goes sort of like you expect. So let's prove that Ramsey class implies modeling property. So this will just be a sketch, because the proof is more or less what we did before. So we did this once for linear orders using Ramsey's theorem, and now we're going to just do the same thing using structures. So consider, so given AI I in I, we want to show that the following is consistent. So we have the partial type in the variables xi, I in I, that assert xi, I in I are I indexed indiscernible, i.e. you say for every phi and for every I bar and j bar with quantifier free type I bar is equal to quantifier free type j bar. You throw in phi x I bar, if and only if phi x j bar. That's the first thing. So this just says your I indexed indiscernible. Whenever I have two intuples from I with the same quantifier free type, then whatever they index have to have the same type. That's the first thing. And the second thing, I need to say that partial type asserting xi I in I is locally based on ai I in I. And how do you do that? Well, you simply negate everything which is never witnessed by an increasing or by an intuple from I. So this consists of not phi x I bar, such that for every j bar from I with quantifier free type, I bar equals quantifier free type j bar, we have that phi a, or I guess we have not phi a j bar. So I guess this negation is sort of not necessary. Okay, so you just take the formulas that are satisfied by every tuple with the same type. Okay, so this is like the analog of the EM type. So the first part says that you're indiscernible. The second part is like the EM type, but in this generalized context. So it's enough to show. Let's give these numbers maybe. Let's call this like 1 and this 2. So it's enough to show 1 is finitely satisfiable in AI, I in I. All right. Now, okay, I think there's not going to be enough time. So this is going to be continued. So what we've done is we've sort of written down a partial type that expresses that there exists an indiscernible object like we want. And so what we'll do next time is we'll prove that that partial type is consistent. And then we'll reduce we'll give the reverse direction. And using that, we will know that we have a whole stock of generalized indiscernibles because combinatorialists have provided us with a whole stock of Ramsey classes of finite structures. So that will be the direction we go. All right, so I'll stop there. Are there any questions?
So
yeah.
Where you defined, right after you defined locally based, we had a remark that I think if BJ is locally based in AI, then BJ satisfies the EM type of AI. And so we need BJ as indiscernible, but not AI, is that right?
That's right. That's right. So I mean, the definition I gave didn't say that BJ was indiscernible. I mean, one sequence can be locally based on another. But oh, I see what you're saying. Yeah. So yeah, yes. Good point. So no. Yeah, I mean, so being locally based, actually, neither of them needs to be indiscernible. So before, what we said is if I hand you the AIs, which are not indiscernible, let's say, then you can find some BIs which are indiscernible and realize the EM type. Now, of course, maybe AI isn't indiscernible, but it realizes its own EM type. So it doesn't need to be indiscernible to be locally based. So the way you should think about it is we have two goals. So I hand you AI, and you need to find BI that satisfy two conditions. One is that the BIs are indiscernible, and the other is that they realize the EM type. And those are independent. You can be indiscernible without realizing the EM type, and you can realize the EM type without being indiscernible. But you really want to achieve both. And I mean, this isn't, I mean, so just to have a simple model in your head, imagine that you have like a theory where the only thing in the language is like a single predicate, right? Now take a sequence where like, let's say the first element is outside the predicate and everything else is inside the predicate. Okay, so if you take a sequence that's outside the predicate, that's indiscernible, but it doesn't realize the EM type. Why? Because it says there are two elements that are outside the predicate, and that's not true in the original sequence. Alternatively, you could take the sequence itself, and that realizes its own EM type, but it's not indiscernible. So what is the indiscernible sequence that realizes the EM type? It's like an infinite sequence inside the predicate. And that, you know, so you have to achieve both.
Great, thanks.
Great. All right,
Nick,
any other questions?
Yeah, can you just state the theorem again, like of Scow, the last theorem, just
Yeah.
state it.
Okay, so what she said is, okay, so suppose you have a structure whose age is a Frisé class. So I'm assuming that means it's locally finite, and L prime is a finite language. So I have and maybe I should have said these explicitly because these are sort of built into my definitions. So you have a structure whose age is a locally finite Frisé class. Then I indexed indiscernibles have the modeling property if and only if that class, its age, is a Ramsey class.
But the terms which are indexed by the sequence come from another structure, right? Like
Yes,
this.
that's right.
Yeah.
Yeah. So I mean, the way of seeing this is, you know, we had this first theorem that if I take a collection of tuples indexed by the natural numbers, then I can find an infinite indiscernible sequence also indexed by the natural numbers that realizes the EM type. This happens to be true because what is the age of the natural numbers? It's the class of finite linear orders. That's a Frisé class that has the Ramsey property.
Mm.
And this turns out to be the general relationship. So for example, if you take tuples that are indexed by trees, then why can you find indiscernibles that are based on those? Well, that's because you have Ramsey theorems for trees like Halpern and Lauchley. Or you can do it for graphs, and that's like Nishitrov-Rodel. So there are these Ramsey theorems for structures, and that implies that certain objects indexed by the structures have indiscernibles based on them.
I see. Okay.
So you've been saying locally finite a lot. Do you mean uniformly locally finite by that?
Yes, uniformly locally finite. Thank you. That's important. So okay, so like in Lynn Scow's paper, what she says is that she assumes that I mean, her assumption is just that quantifier-free types are isolated by quantifier-free formulas, and that the language is finite. But okay, I mean, being Ramsey implies that you have amalgamation. So it's only really interesting if you restrict to the case of Frisé limits. So sorry, she assumes she assumes that quantifier-free types are isolated by quantifier-free formulas and that you're uniformly locally finite. And then she proves that if you have those assumptions, then you're a Ramsey class if and only if this is true. But Ramsey implies amalgamation. So you can go ahead and just reduce to thinking about Frisé limits. And in that case, you know that quantifier-free types are isolated by quantifier-free formulas because that follows from all of zero categoricity and quantifier elimination. So that was the reason the assumption is built in. So we need uniform local finiteness to get an all of zero categorical limit, so that we know that we have this isolation. Okay, so I guess I should end here and enjoy your weekend, and we will pick up on Monday with the proof of this theorem. Okay. Later.